All right, let's just jump right in. I want you to look around you for a second. Everything you see, everything you touch, everything you are, it all runs on a hidden set of rules. It's basically the source code for reality itself. And that code? It's called quantum chemistry.
But, to even begin to understand this code, we have to start with a huge, reality-breaking question that completely stumped scientists for years. If you picture an atom like a tiny solar system, right, with electrons orbiting a nucleus, why doesn't the whole thing just collapse in on itself instantly?
I mean, seriously. According to the physics we all knew and trusted, Newton's rules, the ones that govern baseballs and planets, that little orbiting electron should be constantly radiating energy. It should lose speed and just spiral right into the nucleus in a fraction of a second. And if that were true, well, nothing could exist. Not you, not me, not the device you're watching this on. Nothing.
So, in this explainer, we're going to solve that exact mystery. First, we'll look at the crisis. Then we'll uncover the new quantum rules that saved the day. We'll find out how those rules give every single electron a unique address, see how atoms use all this to hold hands and form molecules, and finally, we'll look at how we're using this code to literally build the future on computers.
So, to put it bluntly, the old physics failed. The rule book that makes perfect sense in our big, everyday world, it predicted a universe that was completely impossible.
And what that meant was that we needed a completely new rulebook, one that was specifically designed for the totally bizarre, counterintuitive world of the very, very small. And that new rulebook, well, that's quantum mechanics. It's really built on 3 foundational pillars. And just a heads up, every single one of them is going to completely defy your everyday intuition. So get ready.
Okay, first up, energy is quantized. I want you to think of an electron's energy not as a smooth ramp, but as a staircase. It can be on step 1, or step 2, or step 3, but it can never exist in the space between the steps. This is the solution to our collapse problem. It can't just spiral down, it has to make a full quantum leap from one allowed step to another. It's also why a neon sign glows that perfect shade of red and a copper flame burns green. Those specific energy steps dictate the exact colors of light an atom is allowed to give off.
Second, and this is where it gets really weird, is wave-particle duality. An electron isn't just a tiny solid ball. No, it's also a wave of probability, just kind of smeared out in space. Get this, it's both a thing and a possibility at the exact same time. It only chooses to be in a single location when we actually look at it. Wild, right?
And that strangeness leads directly to our third pillar, the uncertainty principle. Here's the deal. There's a fundamental trade-off built into the universe. The more precisely you know where an electron is right now, the less precisely you can know its momentum, where it's going and how fast. It's not about having better tools. There is a fundamental fuzziness to reality at this scale.
Okay, so we've got these new, pretty strange rules. How do we actually use them to describe our main character in all this, the electron? How do we pinpoint its identity inside an atom?
We do it with this thing right here, the Schrödinger equation. Now, don't worry about all the symbols. Seriously, just think of this as the master key. It's an equation where you put in some basic information about the atom, and it spits out 2 crucial things: the exact allowed energy levels, those stair steps we just talked about, and a complete description of that electron's wave. Now, that description of the wave is called the wave function, or psi. And this is how we get around that pesky uncertainty principle. We just stop asking, where is the electron? And instead, we start asking, where is the electron most likely to be? If you square the wave function, you get a probability map, basically a cloud showing the region where that electron probably is. We call these probability clouds orbitals. So, the solution to that big equation gives us an electron's unique address, and it's made up of 4 quantum numbers. Think of it like this. N is the main energy level, kind of like the city the electron lives in. L describes the shape of its probability cloud, that's the neighborhood. M sub L tells you its orientation in space, which is like the street address. And finally, M sub S describes its spin, a purely quantum thing you can just imagine as the electron pointing either up or down. And here's the kicker. No 2 electrons in the same atom can have the exact same set of 4 numbers, ever.
And these numbers literally define the geometry of that electron's probability cloud. So for example, when that second number, L, is 0, we get the simplest possible shape, a perfect sphere. We call that an s orbital. But if we bump L up to equal 1,
that cloud changes. It takes on a more complex dumbbell shape, a p orbital, which can actually point along 3 different axes in space.
And as you keep increasing that number, say when L gets to 2, the shapes get even more beautiful and intricate, like these d orbitals that look like clovers. So the electron's address literally spells out this amazing, complex geometry hidden deep inside the atom.
So now we get the geometry of an electron's world, inside a single atom. So, what happens when 2 atoms get close enough for their electron clouds to actually meet? Well, that is the chemical bond. That's how atoms hold hands.
Now, chemists have 2 main ways of thinking about this. The simpler one is called valence bond theory. It basically says that bonds form when these atomic orbitals just physically overlap, kind of like 2 clouds passing through each other, and they share their electrons. But the more advanced model, molecular orbital theory, says something different. It says the atomic orbitals actually merge, they disappear, and they form brand new orbitals that belong to the entire molecule.
So why have 2 different theories? Well, valence bond theory is just fantastic for getting a quick, intuitive feel for the basic 3D shapes of simple molecules. But molecular orbital theory? It's way more powerful. It can correctly predict things the simpler model just gets wrong. It shows how those electron waves can interact. Just like sound waves, they can add up constructively to create a stable, low-energy bonding orbital. Or they can cancel each other out, creating an unstable, high-energy anti-bonding orbital. Okay, so we've got the rules, we have the equations, we even have the bonding models. This brings us right into the modern era, where we can actually take this quantum code and use it to design our world.
But there's a catch, and it's a big one. That Schrödinger equation, it's only perfectly, exactly solvable for an atom with 1 electron, like hydrogen. The second you add another electron, the way they push and pull on each other makes the math, well, impossibly complex for any human to solve by hand. This is the infamous many-body problem.
And that is where supercomputers come in. Chemists basically use 2 main approaches. Ab initio methods, which literally means from the beginning, try to solve the math from first principles. They're incredibly accurate, but they take just enormous amounts of computing power. So the real workhorse of the industry is something called density functional theory, or DFT. It's a really clever shortcut that calculates the overall density of the electron cloud instead of tracking each individual electron wave. And it gives us fantastic accuracy for just a fraction of the computing cost.
And why does any of this matter to you and me? Because by using methods like DFT, scientists can now model molecules on a computer before they ever have to make them in a lab. We can design new drugs that fit perfectly into a protein like a key in a lock. We can develop lighter, stronger, more advanced materials. We can create catalysts that make industrial processes cleaner and more efficient. We can even model totally new ways to capture and store energy.
All of that, every one of those breakthroughs, it all comes from solving that one simple question from the beginning: why doesn't the atom collapse? In answering it, we uncovered the fundamental rules of reality itself. Which, it leaves us with one last big thought. Now that we can both read and write the code of matter, what on earth will we build next?